Let's take a look at a couple of the key points when it comes to scheduling in an operations management context. So start to get our head around some of this. Certainly there's going to be some nuances between scheduling manufacturing operations versus scheduling of services. So we'll kind of keep those two separate, recognizing though that there's some overlap between them. So we'll start out with the manufacturing side and looking at some of the key issues, whether it's a high volume operation, intermediate, or low volume operation. And then we'll throw in the theory of constraints, which applies to both services and manufacturing, although it was developed out of a manufacturing context, and then a couple comments on services scheduling. So get our heads around exactly what this is. Scheduling is at the end of the line because a lot of prior decisions have been made that have affect or constrain what we can do with our scheduling. So scheduling is actually establishing the timing or the use of resources, equipment, facilities, and people, and that is to actually produce the output. So prior to all that happening, we've made decisions about systems capacity, about how our product or service is designed, what equipment we have, how that equipment is organized, worker selection, and et cetera. So there's been a lot of decisions. So we're really at the very tactical end of making it actually happen. So we'll work from left to right, make some comparisons between these. We'll start with the high volume system. So we're looking at a process that creates a lot of output. So when we talk about volume, it's strictly from the account standpoint. They're often referred to as flow systems because we see things like the facilities that create gasoline and other petroleum products, sugar, flour, things like that, that the equipment is highly customized, high volume, low human input. But we might even throw in something like automobile manufacturing, where the processes have been so refined and so automated that the cars come through at a very steady clip. And some of the issues with those really get down to line balancing to ensure that the work is spread appropriately between the equipment, and also if there are human involvement, that there's balance between the work in each workstation. When we move to an intermediate volume, the issues change because we're often talking about the changeover between multiple products. So there's been a prior case where it was introduced and we were looking at cookie manufacturing. And so in this cookie manufacturing facility, we certainly had mixing and cutting and baking and packaging, but we probably don't run 24/7 making all chocolate chip cookies. So we may make chocolate chip cookies and sugar cookies and molasses cookies and oatmeal cookies. So we've got issues when we change over between different cookies, whether we need to clean all the machines, whether we need to just load new inputs into the process, or how that's going to work, because certainly systems work best when we set them up and we let them run for a really long time. But if we do that, we accumulate large amounts of inventory of a single product. So in our cookie situation, where we might have 5 different types of cookies, we need to go through some type of a rotation or a sequencing to ensure that while we want to decrease the run size from infinity down to something more reasonable, we also want to make enough of each cookie that it offsets the time it takes to set up and change over between different cookies or different products. So we're looking for that balance. And often the way we accomplish that is we reduce that setup time as much as possible. And in a cookie example, we might make sugar cookies first because they create they add the least amount of color into the machine, and we might make oatmeal cookies next, and then wait to make chocolate chip cookies because then we're going to get that chocolate smear all over the place. So those type of things to reduce the cleaning time between operations. So we only have to really clean all the equipment when we stop making chocolate chip and move to something else. So those type of decisions to really minimize that time for either what we'd call setup or changeover between products. Low volume would be a job shop operation. So I'd use the term MTO, make to order. So maybe that would be custom cabinets, or it could be an automotive repair shop, or a customization shop, or a group that's assembling computers, and each computer is made specifically by design for each customer. Then we get into the main issues being loading, which means which workstations are going to work on which job at which time, which turns into a scheduling problem and is often resolved using Gantt charts, which if you've done some work with project management, you may have already been exposed to Gantt charts. And here's just an example. And a Gantt chart is simply a combination of work that needs to be done, which are the rows, and then columns, which is the time that they can occur in. And we move these boxes around to see when we have the best combinations. And those X'd out areas indicate when that work center is not available, either due to maintenance or training or some other issue. So we sequence, we move these around. Now this creates another situation, and again we're looking at the unique situations here in low volume, and that is that we need to decide whether we're going to use a strategy of infinite loading or finite loading. Infinite loading means we just start pushing jobs into different work centers and we ignore the capacity constraints. Sometimes that's necessary to more efficiently use our workstations, but that's going to create situations where we're going to need to deal with that overcapacity situation where we might have to use overtime or outsource some of that work in order to get it through. If we use finite loading, then the capacities are honored, and we might have to deal with times when jobs get pushed out way into the future, so we may be delaying delivery of a customer's work, which again may cause us to choose to move to overtime to increase that capacity or to outsource. And here's just kind of two examples. And again, if you've worked with project management, you've dealt with our loading versus leveling operation, because part of scheduling is we would like to, whenever possible, have a smooth flow through an operation, so we're not doing high and then lower volume and then super high volume, and it just gets to be hard to manage the flow of inputs and then the worker interaction. So in infinite loading, we have those issues where we are over capacity, and we have to determine how to do that, whether we delay some of that operation into that period 4 or 5, or we outsource, or we allow overtime. And then with finite loading, we honor those, but realizing this finite loading chart doesn't completely show the issue that jobs will often get pushed out into the future, so delivery will be delayed. Another topic that always comes up in the scheduling issue is the theory of constraints. I believe the author of Theory of Constraints was an engineering fellow from manufacturing. I believe is Eliyahu Goldratt. And he wrote a couple books, which I don't recommend reading. While I really like Theory of Constraints, the books are incredibly painful to read. One book called The Goal I remember in particular. But anyway, Theory of Constraints I like because what it is reminding us is that if we look at a multi-step operation, and that could be a retail store, it could be an assembly line, it could be any type of process where multiple steps are involved. And what Theory of Constraints reminds us is that you need to find the bottleneck operation, the operation that has the lowest capacity potential, because the entire process will be limited or constrained by that bottleneck operation. So it does no good to increase capacity on non-bottleneck operations. It will not increase the throughput or the output of your operation. You have to focus on those bottlenecks. You have to identify them and then do whatever you can to optimize them, use them as well as possible, or if there is any way to actually increase the capacity of that bottleneck. We often hear this term drum buffer rope as a framework to address when you have a constraint. The drum is just the schedule, and when we're talking about drum, it's not talking about something you wind things onto. It's talking about a drum, a musical instrument, where it sets the rhythm of the operation. A buffer is an area where we can gather up materials, and it's normally just outside of the bottlenecks, downstream of the bottlenecks, so that the remaining operation can continue to flow while the bottleneck operation catches up. The rope is the sequencing, or how we pull things through the operation. So again, those bottlenecks, there's kind of a 5-step process. Determine what operation is that bottleneck. Then you want to make sure that you're getting the most product through that bottleneck as possible, whether that means running it 24 hours a day, or scheduling the maintenance carefully, or ensuring that the input products are sufficient to keep it running at its maximum. Then you balance everything else to match that constraint. You don't bother increasing the capacity anywhere else, because you know that regardless of how much anything else can handle, the bottleneck will be the determinant. Then, can you overcome that bottleneck? Can you eliminate it? Can you double the equipment? Instead of having one machine that produces 10,000, maybe put 2 machines side by side, and then you could make that bottleneck go away, and then something else becomes the bottleneck, and you go address that. So that's what number 5 is getting at, is once you increase and maximize that bottleneck, if it is no longer the bottleneck, you move on to what now has become the bottleneck, and you continue to address that until your overall operation output increases. So interesting, and people mention the theory of constraints, or let's say TOC, and it's a good thing to keep in mind. A couple little nuances about scheduling services. Remember, services are a little different because you can't store them. They have to be available when the customer wants them, and also the realization that customer demand has a random nature to it that doesn't come in steadily. We like smooth flowing operations, and that's not the case when you're services. So might have 4 customers come in at once and then no one for several hours. So we have to have a lot of flexibility built into the system, and keep in mind that we're dealing with customers, we're dealing with people who are our actual workforce, as well as any facilities. It says equipment here, but I would say facilities, equipment, capacity, space to be able to handle those customers. Some ways to deal with that issue that's different with services is we might use appointment systems, reservation systems like Open Table and things like that. And then to keep in mind that there might also be cyclical implications for it, where that cyclical work might either help us in giving our employees some relief, so they're on for 3 days, off for 2 days, on for 3 days, or something like that. Or we may also recognize that the demand that comes into services might have more of a cyclical or a seasonal nature to it, where we can adjust the capacity to deal with those variations in the demand. So those are just some things to keep a lookout in the chapter. I will remind you, though, that there are some special situations like the Hungarian model and the Johnson law. So those get a little complicated. That's not what we're trying to get out of this chapter. We're trying to just get a grasp on what are the key issues around scheduling, not necessarily getting into the weeds of executing the Hungarian model or applying Johnson's law.